The next speaker is Kylie Cow.
Okay.
Yeah. Okay. Excellent.
This work? Can I put it on my pocket? Hello?
Perfect.
Great.
Next one is Kylie Cow.
Oh, all right. Hello, everyone. Thanks to the organizers for giving me this great opportunity to learn about time domain science and also talk about my work. I'm a grad student at the Ohio University and will join University of Michigan as a postdoc later this year. I know nothing about college football, just a disclaimer. All right, so I am a member of the high latitude imaging survey project infrastructure team. So if you are familiar with the Roman terminology, you may wonder, okay, high latitude imaging survey, great, but that's about weak gravitational lensing cosmology. That's a static feature of the universe. But this conference is about time domain science. So did this guy misread the title of the meeting? No, because I do want to share my image processing techniques with the time domain community. So the title of my talk is hot wiring the Roman sky. What's wrong with the Roman sky? Of course, the sky is not wrong. And there are some imperfections about Roman. So we know that the Roman Space Telescope, specifically its wide field instrument, has very high spatial resolution. It's the same as Hubble, 0.11 arcsecond per pixel. However, that is still not enough to fully resolve the point spread functions given the bands it operates in and given the diameter of its aperture. Therefore, we say that the Roman point spread functions are undersampled. So if we ask Max Yuda, he would say, oversample we must if we want to do precision measurements. With undersampled point spread functions, if we do observations like interpolations, then we get all sorts of weird things. So, okay, sorry for the formatting problem. This is function. So basically, we have been using this IMCOM software, which originated at this exact institution 15 years ago. So basically, what it does is it allows you to set your the point spread function you want, and then it does some linear algebra to render that point spread function as possible as it can. So here we have a, is this a laser pointer? Great. So basically, in the high latitude wide area survey, which has two components, the imaging survey is one of them. So we usually have two passes and each with 3 dithers. And since we are doing weak lensing, we do not care much about time domain. So we just combine the images to make an oversampled image. So the traditional way of doing this is using the software called Drizzle. It has been widely used for Hubble and JWST. However, if we do that, we see that we can see a hexagon because it's doing things like interpolations and we get all sorts of residuals. So, but if we do IMCOM, we get something much nicer. So as I said, we combine the images because we don't care much about time domain information. If you care about time domain information, you can just choose to use one single image as the input and get a good PSF. So why hasn't the community been using this software for image processing? The problem is about efficiency. So actually 2 years ago, right after my talk, Dr. Christine McQueen asked me how fast is IMCOM, and my answer was disappointing. It's still like 3 or 4 orders of magnitude slower than Drizzle. Although we have been working very hard to make it faster, it is still like 2 or 3 orders of magnitude slower. So if you have a single CPU core and you want to process one single Raman wide field instrument image, which is 4,000 by 4,000 pixels, or 7.5 arc minutes by 7.5 arc minutes. It will take about an entire day to do that. But today I'm going to advertise something new. I call it Fast IMCOM, and it is significantly faster. And I think this efficiency makes it at least eligible for time domain image processing. Well, about 2 months ago, after I said this at AAS, people asked me, okay, how did you achieve that? So I don't want to go very technical, but I do want to give a brief explanation. So basically, IMCOM is an optimization process. How it works is to build large linear algebra systems and then solve them. And how Fast IMCOM works is to directly give you the solution. Because I made an intuitive guess, and it turns out that the intuitive guess is quite good. Okay, so if you are interested in technical details about image processing, I'm very happy to talk about it after the session. So here is an example using open universe simulation. So these are simulated highlighted imaging survey. So unfortunately, we only have 5 or 6. I think here we have 5 single epoch images for the same area. But as you can see, now I have unified the pixel grid, and I have also unified the point spread function of the single epoch images. So if we want to do pixel by pixel level comparisons between the epochs, then the process is facilitated. Of course, this is just a demo. It is really hard to see whether it actually facilitates detections, but that is my hope. To support that statement, I did some measurements on noiseless point sources. Of course, the actual point sources are not noiseless, but I just want to show that this image processing or image reconstruction process is not introducing systematics into our signal. So here, blue is measurements on IMCOM. PyIMCOM is just the Python implementation of IMCOM. So basically, the blue data points are from the combination of 6 images, and the green and orange points are from single epoch images. So basically, my conclusion is that if we want to have high precision, high accuracy photometry and astrometry, Fast IMCOM is eligible for that. And another thing I learned from past 2 days is that star galaxy separation is something of interest to the time domain community. So fortunately, I also have that. So on the, okay, this is not a straight line. Anyway, so on the y-axis of the first plot, I have the width. So basically, although we have point sources with the point spread function, it's a distribution. So we can measure the width of the point sources. It's not contradictory. So basically, we see that the width measurement is also very accurate and precise. That's why I think if we do image reconstruction with these tools, it may benefit star galaxy separation as well. But of course, I'm new to that term, so that's something to test out. Okay, I'm very, very glad that Rebecca has already presented these 2 things, so I don't have to go through them. But with this slide, I want to talk about the potential applications of my image processing tools for the time domain community with focus on Roman. So I think the first thing is that after unifying the pixel grid and the point spread function, we can do pixel level comparisons. That facilitates the setting up of reference images. And the second part is, I think we have also heard about this earlier this morning. So a great feature of Roman is that it can go to relatively high redshift. So for high redshift, if we want to do image stacking, then the tool I'm talking about may be a good choice. So, okay, I think this is the second to last slide or something like that. So basically, this new tool goes beyond Roman because it only needs good measurements of the point spread functions to operate. So if you have, for example, GWC images or Hubble images for which we have relatively good PSF models, it can also work. And even your instrument is on the ground, but you believe you can have good measurements of the PSS. For example, for Rubin, I think the case is that you have a small telescope for guide stars or something like that, so that you expect to have good PSF models. Then this tool will also work. So to conclude this talk or advertisement, I would like to clarify the inputs and outputs of this tool so that it may help you think about whether you can actually make use of it. So as inputs, it needs calibrated single epoch images, or in the Roman terminology, it's called L2 images. And it needs good word coordinate systems, basically the mapping between pixels and locations on the sky, and also measurements of the point spread functions. And as a reward, you can specify the pixel grid you want and the point spread function you want. But however, the point spread function you want needs to be slightly wider than the input point spread functions for the mathematics to work. So, okay, I have been working on the papers, but that's not the point. So the organizers have asked us to relate our talks to some key discussion points. Unfortunately, I'm new to time domain astrophysics, especially transients. So I think I can only relate this to how do we optimize transient discovery with multi-wavelengths and multi-messenger alert systems, or maybe streams. So basically, I think the main benefit is that with aligned pixel grid and point spread functions, maybe we can reduce the rate of false alarms. So that's why it's related to this question. Okay, thank you.
Thank you very much. Any questions? Yes.
Amazing work. I have a question. Do you think there is still space to improve the performance? I mean, you went from 1 day to half an hour, which is amazing, but it's still half an hour per detector. Do you think there is like potential for further improvement?
Yes, for sure. That is actually a very great point. So basically, this half an hour performance is for the requirements of weak lensing. And currently, I'm doing interpolations using a 10 by 10 pixel grid, grid in the oversampled functions. But if we reduce that to, for example, 6 by 6 or 4 by 4, I think we can make it significantly faster. Because I understand that in alert systems, there are other systematics. So as long as the different systematics are comparable, it is well acceptable. So yes.
Any other questions?
Similarly, if you move to GPUs,
I don't know about GPUs, unfortunately, but if people want to help me with that, I'm happy to try it.
Any other questions? I had a question about your amplitude and width measurements. If you could go to that. Yes. It seems you have really like an offset for like the IMCOM with respect of your Fast IMCOM. Why do you think that there is an offset?
Okay, that is a very insightful question. So when we do the PSF reconstruction, we can only try our best to construct the PSF specified by the users. But this process is not perfect. So we use PSF residuals to refer the discrepancy between the actual reconstructed PSFs and the user specified target PSFs. So I think such gap is caused by the shapes of the PSF residuals. So actually for the Fast IMCOM results, I used the knowledge about PSF residuals to calibrate the results. And with IMCOM, because the image have been combined, it's hard to do such a calibration. So that's why we see a gap here. And also we see some remaining correlation between the measurement errors. So I think the calibration process has some further room for improvements.
Thank you. Any quick questions? Yes.
It's good to have some more complicated method like this, but I wonder for Roman If you do 2 frames in the same position because it's dithering a lot, the target will be different position in the detector. But I recall the LSST had 2 frames, like 15 seconds, at the same field of view. So you can subtract directly know, transient. So something like that might be helpful without complicated, method. Eventually, you might have to do that for accumulated image.
Thank you. I acknowledge that it is something new, and the talk is not about replacing existing tools with something new. It's about advertising a complement to existing tools. Thank you.